Okay, so we have more problems. So this is number 6. So evaluate the integral, the double integral over the region D, which we will describe in a minute. The function y square e x y dA. Okay, so dA is, technically we read it as the incremental area element. So it, when you put coordinates, it's either going to be dx, dy, or next week we'll pass to polar coordinates, then it will be dr, d theta. Okay, where D is the region, of course, in R2, bounded by y equals x, y equals 4, x equals 0. Okay, so again, we'll sketch the region. The region will be, again, something simple like this. Otherwise, the problem does not work nicely. And here, okay, so we probably want to integrate with respect to what first? Which one do you prefer to integrate first? Well, the true correct answer is who cares? But we have to force ourselves. Okay, so if you have to, you'll probably choose to integrate with respect to x first because it's easier. Okay, so first let's sketch the region. So the region, if I have given the description correctly, x, y. So I have this y equals x and y equals 4. X equals 0 is this line. Okay, so you see we have 3 lines there. This is one line, this is the other line, this is the other line, so this is the region. Okay. So let's denote the significant points. Points of intersection are significant, so this is apparently 4, 4. This is y equals 4, this is 0, and this, well, I don't think we'll need this, but since we are going to integrate with respect to x, we don't need this number, but it's 4. Okay, so we set up the integral y squared e x y dx dy. Okay, so let me check what I do after this. Okay, so I'm integrating with respect to x, so I keep doing this. I keep saying this so that it will become a habit. I integrate with respect to x, so I consider an arrow, a general arrow parallel to x-axis. It enters the region when it cuts this curve. This curve is x equals 0 curve. Okay, so x equals, let me emphasize it this time, x equals 0. It leaves the region along this curve. Here I solve for x. Okay, so this is simple. There is no solving, but this is the general procedure. Here, this may be a complicated expression. You have to solve it for x around here. Okay, so for example, if it has square roots, etc., it has plus square root, minus square root, and you decide whether this is plus or minus, just like we did in one of the examples before. Okay, so here it is easy. I solve for x, x equals y. Okay, so that corresponds to this. Then I consider moving this line. I made a promise here. I said that this arrow will enter the region along that curve, leave the region along this curve. So for which values of y, for which position of this arrow, this promise is correct. Okay, in this case, it turns out that all the way from 0 to 4, this holds. Okay, so again, just to emphasize, it is nice to show these things in simple problems. So it starts from y 0, it goes to y equals 4. And we do our final check. The last thing here must be numbers with respect to x and y. No x and no y should appear here. Okay, I have 0 and 4. So, okay, all the trivial things are checked. Now I integrate this. Okay. So I have from 0 to 4. What is, well, here, since I'm integrating with respect to x, this is my function. So antiderivative will be e to the xy. Okay. If I take its derivative, I'll have y times xy, but I have y squared here. So I put another y here. I take its derivative with respect to x again to check. Okay, so if I take the derivative of this, y comes in, I have y squared, so I get this. Okay, so this is the antiderivative. I have to evaluate this from x equals 0 to x equals y. And after I do that, I'll integrate it with respect to y. Okay, so now 0 to 4. When you put x equals y, you get y e to the y square. Okay, so we can integrate that. When you put x equals 0, you get just y. So minus y dy. Okay, so we'll look at here. This is something we can integrate. So this is probably going to be 1 over 2 e to the y square. I take the derivative of this. This 2 is killed with this, and I don't have anything here. Minus 1 over 2 y square. I take the derivative of this, I get this. So this whole thing is from 0 to 4. Okay, so you just put in values, and I put the values here. So this is 1 over 2 e to the 16 minus 17 over 2. Okay, so this comes, this 17 over 2. Okay, so this thing comes because here you have some number, 16 over 2, and then you put 0, this becomes 1. So 1 minus 16 over 2. Well, the 0 also comes with a minus sign here, so you add 16 and 1. Okay, so that's why that number comes. Again, you don't have to approximate this. This number is approximately this thing. 1 over 2 doesn't matter, so it's approximately 4 times 10 to the 6. Okay, so you see this one is just a detail. Even if you are sending a rocket to Mars, you don't need that much precision, because in space, who cares about this detail? Okay, you just head towards Mars and eventually you are there. Okay, so this is how numbers behave. Okay, so next question is find the volume under a given surface above a region, again described by some curves. So the problem here is to find the curve properly. Okay, so let's do it over here. So this was a volume question. We'll have another volume question. Find the volume under the surface. Okay, so this pen will not stay with us. Under the surface, z equals 2x plus y square above the region. Okay, it is understood that above the region in the xy plane, bounded by x equals y squared and x equals y cubed. Okay, above the region, so it is understood that this is xy plane, that is z equals 0. Okay. So the challenge in such a problem is to sketch the region correctly and set up the integral. Once you set up the integral, the rest is easy most of the time. Okay, so I'll put x, y like this. Okay, so what is x y square? It's a parabola, right? And the parabola lies on this side, okay? X equals y cubed is a cubic thing. It will be like this, okay? So it will only intersect our parabola somewhere here. So our region will be here. So I don't bother drawing the parabola here. So I'll draw the parabola like this, x equals y square. I can intersect these two curves in my mind easily. When x equals 0, they intersect. And what other point they intersect trivially? 1. And between 0 and 1, which one is larger? Y square is larger. Okay, so x is... Okay, so how do I draw this? You tell me. You are waiting for me to do this, but I'll pretend that I'm sipping my coffee. Okay, so since I'm drinking coffee, you are free to bring coffee to class every time and drink. Yes, there are two chances, right? Okay, one of them will be like this, the other one will be like this. So, which one is it? Okay, so I'll draw two things. So one of them, the curve comes like this. Well, okay, it has to be all concave down, but... Okay, so one of them is like this. This is x. Of course, it doesn't go down, but I'm writing it y cubed. And the other one will be like this. So this is fatter. Y equals x. No, x equals y square. X equals y square, and so the other one is x equals y cubed. Okay, so you decide which one is which. So here, let's say y square one we are drawing with black. Of course, this is not going down, but I just put it this way. And here, the black one is this. And we all agree that this is 0, this is 1, 1, this is 0, this is 1, 1. Okay, so which one is correct? Which one is the curve? Okay, you see. Huh? Right one? Why? Okay, convince us that this is the right one.
X row is bigger than 1 given the function.
Okay.
Y cubed is bigger than y squared.
No, I'm not. Let's do it with y because y is the parameter. Okay, so here, let's. So you want something larger than 1. So we take 2 here, for example. Okay, so which one? Which one? If you take y equals 2 here, you consider this line, so it will intersect these. Okay. Which one will it intersect first? It will intersect y squared, so it must be this one. Okay. Okay, so does everyone agree? Okay, you object, you tell, okay. Between 0 and 1, you want to draw this. Okay, so suppose this is 1 over 2. Then if y is 1 over 2, so if y is 1 over 2, this is x equals y squared. If y is 1 over 2, this is 1 over 4. And x equals y cubed, this is, if this is 1 over 2, this is 1 over 8. This is smaller, right? So when I go, I should first intersect the y cubed one. Well, here I'm intersecting this one. Here, first I intersect the y cubed one. So again, with your argument, this is correct. With your argument, this is correct. So 2 people are voting for this. Shall we have democracy? No, nobody wants democracy. Okay, so mathematics is dictatorship. If it is correct, it is correct. So this is the correct one. Okay. Okay, so this is our region. Let's color our region red. Now that we are confident, we can draw it like this. So this part doesn't matter for us anymore. Okay, so we'll set up the integral on this. The height function is given. Okay, so on this part, you see here x and y are positive. So the surface is not going down xy. That you should also check, because if volume is asked and if the surface cuts the xy plane, what remains under the xy plane will contribute as a negative volume if you integrate it. So if you want absolute volume, then you should find the region where it is above. You calculate that. You find the region where it is below. You calculate that separately. It will be minus. You take its absolute value to get the volume, and you add this. If you want to find the volume, absolute volume bounded by this surface and the xy plane without any signs. But here we check that the surface is always above xy plane. So we just integrate that function over this red region, and we are hoping that we can evaluate it and find the number. The number will be volume. Okay, I'm doing these things in a long-winded way, but these are the things that should go through your mind. Of course, normally after you get experience, these pass through your mind in a split of a second, but this is what you should consider, because if you catch something which is wrong with the problem, then you have to change your argument. Okay, so now everything makes sense. We just set up the integral. Okay, so what was the question? The volume. So volume is equal to double integral. This is the height function. Height is 2x plus y squared. Obviously, it doesn't matter whether I integrate this with respect to x or y first, because it's a polynomial. Both ways, I can find an antiderivative. So if I'm being lazy, if I want an easier integral, I look at the region, which way it is easier to write the boundaries in this region, whether I go with respect to x or y first. If I integrate with respect to y first, I have to solve these equations in terms of y. But they are already solved in terms of x, so why don't I do integrate with respect to x first? Okay, so I take my arrow parallel to x-axis. All the solutions are already there. So I integrate this with respect to x first. I first enter the region with y cubed. Then I leave the region at y squared. And this holds between 0 and 1. Okay, this 1 and this 0. Okay, if we do this, this is 1. So this description holds between 0 and 1. 0 and 1. Okay, so this is, as a human, your responsibility. Unfortunately, there are not any software yet where you read this question and comes up this. Okay, so as I mentioned last time, this is your responsibility to make life easier. Every time a new development comes, we hope that the calculus book will become thinner, but over the years, the calculus book becomes thicker and thicker. I don't understand why. Okay, so this is easy. So I'll just write the answer for you to check. This is 19 over 210. Okay, so there's no challenge here. This is dy. There's no challenge here. You are just integrating a polynomial. Okay, so the last problem before we say a few words about polar coordinates is, so this similar thing. Find the exact volume of the solid. This is from your book. Under the surface z equals x cubed y 4 plus x y cubed above the region bounded by the curves y equals x cubed minus 1 and y equals x squared plus x for positive non-negative x. Okay, so you look at the problem. If I set up the region, if I sketch the region and set up the integral with respect to y, apparently it will be easy because the curves are already solved for y. Everything is a polynomial. And if I set up the integral, evaluate, I get exact value. So why is it mentioned in the problem that you should not shy away by an approximation, but find an exact value? So there's something fishy. We just make a mark in our mind about this, and we proceed because everything looks totally trivial. Okay, so let's sketch the region first. Okay, so we sketch these two regions. You see this is always positive. It's a parabola. It starts from the origin, since we are only looking at x equals positive. And this is a usual cubic, but it starts from minus 1 when x is 0. So the curves are something like this. This is the parabola part. The other one, again, you see at x equals, one of them is minus x. This is minus x. Okay, so again, it starts from the origin, okay, but when x is less than 1, this is less than x cubed is less than x, so it is negative. And it is 0 when x equals 1, okay, so it's something like this. So this is 1. So this curve is y equals x cubed minus x. This curve, the other curve here is y equals x squared plus x. This point is, well, I found this 2, 6. So I'm, this point, so I don't think we'll need that point. Okay, so I'll leave it there. So this point is 0 because we decided to integrate with respect to y first and everything is solved, so no problem. There is little hope of integrating this with respect to x first because this region is okay, but here you see you enter this region by this curve. This is one of the cubics. You have to solve this for x in terms of y, which is very complicated. And then you have to choose the sign so that you express this one and this one separately. Okay, so y go into that. We integrate with respect to y first. So if we take an arrow like this, it already intersects the region here, leaves the region here, and this description is valid up to this point where x is equal to 2. Okay, so volume is equal to, the function is this, x cubed y4 plus x y cubed. I want to integrate with respect to y first, then x. Y starts from x cubed minus x goes to x squared plus x, and everything between 0 and 2. Okay? So you look at this. It's totally trivial. Y emphasizes. In fact, there was another word here which I didn't write so as not to scare you. It says use a computer algebra to calculate this. You say, oh, I can do this by hand because this is a polynomial. Okay, so when you integrate this thing, these are polynomials. These powers will increase by 1. And inside y, this is going to be y to the power 5. There you are going to put these things. Okay, expand it, integrate it. You'll get even larger powers, lots of coefficients. Okay, so that's where you need a computer algebra. You can theoretically do it by hand, but then after you finish doing this, nobody will talk to you because you'll start talking strangely. Okay, so use a computer algebra system as they use. And the answer is, now I'll write the answer and you'll understand why this is. This is 2,958,004,000 470,896 divided by 2,990,907, which is approximately 1,060. That something. Okay, so theoretically it is easy, but practically you have to use a computer. Okay, so this was the fun part. So so that finishes our training with double integrals in x and y. Yes?
How do we get rid of the minus sign below the x?
Well, we are not using the sign. We are just using the equation of the curve. Equation of the curve is y equals x cubed minus x.
But y equals x minus x is negative between 0 and 1.
Yes, that's why I drew the path here. The curve is here. This is our region.
So isn't the problem that we couldn't calculate the absolute volume?
Well, I didn't check that honestly, but I assumed that this is positive. Okay, so check that. Check if this is positive on the region. Okay, so you are right. We have to check this. So I did this calculation assuming that that's always positive. Okay, so I was fooled by the fact that everything is plus there. But when y is negative, we'll have a negative here. But okay, so I will check. We have to check. But I suspect that, first of all, since this is an example in the book, there is no such trick. This seems to be the only trick. Okay. If it is negative somewhere here, then we have to cut it like this, and it will be more complicated. Okay. So, other questions? Okay. Now I'll remind you very briefly about polar coordinates. Everybody knows polar coordinates, but technically we have to remind you about this. Next week, on Monday, we'll do double integrals in polar coordinates, because most of the scientific formulas, most of the scientific models are quadratic. You have x squared plus y squared. Most of these things are like that. In fact, we teach you lots of differential equations in the next year. But again, most of the differential equations in everyday life of a scientist or an engineer are second-degree differential equations. Okay, so polar coordinates, even though they look very special, they become very useful. Because when you have x squared plus y squared, which is very difficult, if you have e to the power x squared plus y squared, this shows up very often. You cannot integrate it with respect to x or y. You change to polar coordinates, it suddenly becomes e to the r square. As a miracle, dx dy gives you an extra r to integrate that. Okay, so that's what we will talk next week. So let me briefly, if I take it long, remind me, I'll give you 10 minutes for the quiz. So a short review, very short review of polar coordinates. Okay, the geometric idea is this. These are Cartesian coordinates. If I have a point here given by x, y, I want to describe this point in a different way. Giving a coordinate is an address. Okay, so you give this to a person, x, y. Okay, so you read this x, y as follows. I'll go by x distance here, then I'll go perpendicularly y distance. That's an address. So we'll give you a different address to reach the same point. So the idea here is to take this, and this is, in calculus, this is directed. So this can be negative here. Okay, and we also consider this angle as theta. Okay, so we say that this is going to be, we call this r. This is, okay, so take this equals means that the same address as, they are not just algebraically equal, are theta. Okay, so as addresses. Okay, coordinate is address. The only thing that the only thing that you should keep in mind here is that the address in Cartesian coordinates is unique for a point, but in polar coordinates the address is not unique. So for example, consider this angle. What is this angle? Theta plus pi. Okay? So the same address is minus r theta plus pi. Okay, so how do I read this address? This says start from the x-axis, go theta plus pi, and then turn back and go a distance of r, assuming that r is positive. Okay? But we also know that if I can turn around this once, come here, and then go here, so this is the same thing as r theta plus 2 pi. Okay? Or r theta plus 2 and pi for any integer z. So I can turn around this backwards, and I come here, I go theta. Okay, so this is just the main thing that you should keep in mind. Something which becomes useful very rarely is the notion that there is another, when you change coordinates, you suddenly have another Cartesian coordinate. Okay, so actually, this is what's happening. We have a new Cartesian system, r theta. Okay, so these descriptions are actually happening here. Okay, but since since we use polar coordinates to describe something which is very difficult in Cartesian coordinates, we try to impose the two figures here. Okay, we try to understand everything here. But when it comes to algebraic calculations, at some point, if you get confused here, you should also always remember that there is this part here. So, for example, what does this say? If this is theta, if this is your theta plus here, and if you have, so this point corresponds to this point. So this says that if you go up, this point also corresponds to that. Okay, this point also corresponds to that. Okay, so this is just an algebraic picture to keep in your mind, so that when you algebraically get stuck, if you remember this picture, then things will clarify. So actually what's happening is that we have this coordinate system, xy coordinate system, we have r theta coordinate system, and we have a map from here to here. Okay? So given any r theta, we have this usual map. Let me write it in x. Everybody knows this. X equals r cos theta, y equals r sine theta. Okay, so that we can read from here. You have this right triangle. So from here, we have that x squared plus y squared is r squared. So this is the basic reason why we are using this. Then x over y, or y over x is the tangent. But I will not write it because sometimes it becomes infinite. Generally, we are not interested in the tangent of this. These are the two equations that we are using. So let me give a few examples. Nice example. There are one or two polar equations that you should immediately recognize. Well, if you don't recognize that, you can always sketch them. But just when we say y equals 2x plus 1, everybody knows that this is a straight line. Okay, so there are a few things like that you should recognize immediately. So, for example, r equals 2 cos theta. Okay, so again, r equals 2 cos theta is some curve here. Okay, but we are trying to impose it over here. So you look at this thing. When theta is equal to 0, this is 2. When theta is increasing up to pi, this decreases from 1 to 0, so this decreases from 2 to 0. Okay? So it becomes like this, and it becomes like this. It's a circle with center here. So how do I know that? I multiply both sides by r squared 2r cos theta. Now I use these. R square is x square plus y square, and r cos theta is x. Okay, so this is now x squared plus y squared equals 2x, and this is the equation of this circle. Okay, so another thing that you should immediately recognize is 1 plus cosine theta. So you again do this with the same consideration. When theta is equal to 0, this is 1, this is 1, so it starts at 2, and then it decreases. When theta is pi over 2, this is 0, but now then this is 1, so it intersects the y-axis at 1, and then it becomes 0, it becomes negative, and it goes to minus 1. When it is minus 1, when theta is pi, this is minus 1, 0, so it intersects here 0. So the picture is something. 10 dakika doldu. Peki şunu da çizeyim, bitirelim. So this is a highly exaggerated picture of this thing. If you sketch this on a one-to-one paper, you will see that it doesn't look like this. This part looks almost like a circle, and this part is just something like this. But since this is the ideal picture of a heart, this is called cardioid. Take any biology book and look at the shape of a heart. The actual heart has nothing to do with this, but we idealize these things. So here you can have, by changing this plus to minus, you can change this. And you can have, instead of cosine, you can have sine, because you see they behave the same. You'll have this picture turned around here. Okay, so I'll leave the other pictures to you. While you are having a quiz, we can have this. Okay, so that's the end of today's lecture. We'll have a quiz. The quiz is about changing the order of integration in double integrals.